In BLDC, the rotor carries the magnets and the stator carries the winding. We talked about motors that go in cobots in the last video. The same motors are also heavily used in EVs. However, when we go to drones, it's still BLDC, that is, the rotor still carries the magnets and the stator still carries the winding, but now the rotor is on the outside and the stator is on the inside. Mainly because drones need direct drive, that is, no gearbox between the motor and the propeller. The magnets sit at a larger radius and gives enough torque without needing a gear reducer. Plus, to attach the propellers, you need enough surface area to grip for the torque to transfer. But that leads to its own unique problem: heat. The stator is no longer able to radiate heat to the environment. The only channel to conduct heat is the shaft attached to its body. That's why winding quality is even more important in drones to have minimum resistance. And since you need the drones to be lightweight, you can't use hairpins. The small motors won't give you enough space for copper bars to fit. So what's used are round enameled copper wires wound densely through the automated machines, which have to be fine-tuned carefully and customized for every motor design. You can't pull the wires too much to risk losing the insulation and cause short circuit, and it cannot be too loose to impact the efficiency. The tension has to be kept optimal. Again, here too, China has the edge over the cost and scale. In the last video, we used a motor with 48 slots and 8 magnetic poles, which is one common configuration for EVs and robots. But for drones, the standards are 12 slots with 14 poles, or 9 slots with 12 poles. The magnetic poles are more than the slots available, but you still follow a 3-phase architecture. So in a 12 slot 14 pole drone motor, you will have 12 iron teeth around the stator. The slots are the gaps between these teeth. The copper wire is wound around each iron tooth in loops such that your one side corresponds to a north pole and the other side corresponds to the adjacent south pole of the magnet on the rotor. But why a fractional slot design? Why more poles than slots? See, when the slots perfectly align with the magnets, they snap to that position. The more slots that align, higher the snapping and thus higher the mechanical resistance to rotation. This is called Cogging torque. For a 12 slot 14 pole design, your greatest common divisor is 2. This means only 2 magnets ever align with the teeth at the same time. The other 12 magnets are all at slightly different angular positions relative to their nearest teeth. So their individual cogging forces mostly cancel each other out, leading to a smooth vibration-free rotation. Each stator tooth gets its own individual coil, so you don't have layers in the sense of hairpins, but the loops stack up densely, which is again where China's dominance comes in, because what you need is an orthocyclic winding pattern to concentrate as much copper as possible in the limited space. You can't do a random pattern which will lead to higher resistance. You then accordingly also have to optimize the thickness of the wires for the number of turns or loops around each tooth. After winding, the stator gets varnished just like we discussed previously. Then you need your electronics to be properly aligned through the controller software to make the currents toggle across the 3 phases to maximize efficiency. By the way, this cogging we discussed also happens in EV motors and robotics. You just have to use all sorts of tricks to manage that. More on this later. In drone motors, there is something called a kV rating. Changing magnetic field induces EMF. The faster the rotor rotates, the higher back EMF it induces in the stator, opposing the supply voltage. So the maximum speed a motor can reach without any load connected to it is when the back EMF equals the supply voltage. That is when the motor can no longer accelerate and cruises at the maximum rotational speed. kV is simply the ratio between the no load speed and the supply voltage. The kV is a property of the motor itself. It doesn't change when you change the battery. What changes is the top speed. What determines it? the winding, more importantly, the number of turns. But the kV preference is based on your output requirement. Speed trades off with torque. Fewer turns means lower back EMF, which means higher kV and thus higher speed, but lesser torque, and vice versa. A drone doesn't fly because of its motor, it flies because its propeller pushes the air downward. The amount of thrust a propeller produces depends on two things: how big it is and how fast it spins. Moving a large volume of air slowly is more energy efficient than moving a small volume of air fast. It's called the actuator disk theory. But large propellers come with a cost. They need more torque to spin and they can't change speed quickly. So your application determines whether you need high kV or low kV. The battery capacity, the maximum session length, the payload capacity, the responsiveness, etc. The real decision tool is thrust to weight ratio. That sums up the mechanics of drone motors. Next, we'll talk about the electronics. See you soon.